I'm going to go fairly quickly through 8.3 because 8.3 is just titled logarithmic functions, which I know that was a pretty big unit in Math 30, correct? You guys didn't like them, but it was still a big unit. Okay, and why do you think it's in Chapter 8? What did we just do, 8.1 and 8.2? Exponential, right? And logarithms are forms of exponential functions. They're just written differently. Okay, so just to refresh here, so here is your, we talked about this yesterday, so when b is bigger than 1, you have the upward motion, okay, the upward motion of your exponential graph. Okay, that was from Tuesday. And then you have your downward motion if it's a fraction between 0 and 1. That's just kind of so you know the general idea what the picture is doing, and that can help you with your limits or trying to figure out what you're approaching, okay? And so these are inverses of each other. Okay, and we'll talk about that a little more here in a second. Okay, so this is kind of a review from yesterday. Now we're going to talk about how the logs relates to this. So, thus the definition of logarithm function has the inverse of the exponential function means the following. So, remember, log b to the x equals y is the same thing as b to the y equals x. That's the relationship of logarithms. So, easier way of maybe saying this, b, which is the reason I have it this time, which actually makes mathematical sense, is your base. Okay, b is the base of your exponent and your logarithm. Okay, y, this is the exponent piece. Okay, and then they equal whatever you're taking the log of. Okay, your x there. So that's kind of your pattern for logarithms, how they break into exponential functions. So, y. Okay, so just a quick example, if I had log 10 of 3 equals 4, okay, that means I have, which is not right, because I just made it up, 10 to the 4th is, let's just actually make it correct. Let's do 100 equals 2. Okay, so if I did that, just putting it into our form, that means 10 squared equals 100. 10 squared equals 100 in terms of the logarithm pattern. Okay. Okay, a couple things that are important to know is if you're taking, these two things are really going to help you in calculus with simplifying and solving. Okay, a lot of times you're going to have things where you're solving for logs or whatnot, you know how to get rid of things. Okay, for example, if we, and this is what you're going to do a lot with, when we have a base with an x up here, and we need to get that x down to solve. We can't square root, we can't x root to get rid of it. So we need to use logarithms to help us with that. So that's what these are showing you, is that, just so you know, like log, this, I'll put it in numbers for you. Log base 10 of 10 to the x is just x. The bases cancel. What's that? Yes. Because what's your log rule that you can do with exponents? Not add, drop to the front. Remember, your exponents drop to the front, and then you'd have log 10 of 10, which log 10 of 10 is 1, which now it equals x. Okay? So that's just kind of a quick hand. Does anybody want to refresh on that? Because this is, again, I'm kind of going a little bit faster because I'm under the impression that you know some of this. Right. So, but again, the quick way, Morgan, is that anything base to that log with the same base simply cancels, and that number drops down. That's the way you're going to be doing with us, because we know this, okay? But you just talked about, again, the proof for this, if you want to talk about what Morgan's saying, is that we can drop this, the proof for this one. Yeah, wait. Yeah, you do drop in front. I'm just trying to remember. Just 1 second here. Okay, so yeah, so that's what we're going to do. So what you're going to do on this here now, like again, just to prove this, you would log both sides. So that's what I did right here. I logged both sides to bring this down. That's right here. divide this off. So you'd have, I need more room here. You would have log base b of x equals log x over log b, which those are equivalent. Okay, and you'll see that on like slide 11 here for change of base. That's how you change the base. This one? Oh, here? Yeah, so we'll probably log both sides. Yeah, so, but what I'm telling you is you don't have to do that every time. Okay, what I'm trying to tell you is that log base to the same base, that's just going to be canceled and you're going to get x. Okay, again, that's because the x drops in front, log 10 of 10 is 1. This right here, this is going to cancel, you're just going to get x, because 2 log 2. Right, you don't have to do the proof, I'm just showing you how, I'm not just making it up. So, okay, all right, so a couple other things here. So recall that if we have a one-to-one function, you have the domain and a range. Okay, so we have right here, this is the b to the x. Okay, this is log b to the x. So you can see that they cancel each other. Things that multiply each other to get you 1 are inverses of each other. 1/3 and 3 over 1, etc. They're inverses. So here's how your b to the x grows. This is how your log grows. So the reflection line is y equals x. Okay, just kind of knowing that in terms of the how they're growing. But you can always test stuff. Okay, like why is this right here? Why does that make sense for a log? How come that makes sense? So at 1, you get 0. Why does that make sense? Other way. If you put something to the power of 0, you get 1, right? Because this is y, so my y is 0, right? My x is 1. Okay? So what that's saying is b to the 0 equals 1, which anything to the 0 power equals 1. So all your logs are going to have that kind of pattern there. And that kind of give you an indicator of how things are growing. Okay? Vice versa, same thing here. When y is 0, or excuse me, when x is 0, you get 1. That's why it's inverses. Remember, inverses is what? Switch x and y, you'll get you the inverse, and then solve for the whatever you're trying to find the inverse of. Okay? Any questions? Still doing okay? All right. Okay, so a couple things to refresh as well. Anything logarithm of 1 is always 0. We just talked about that because anything to the power of 0 is 1. So the x-intercept of the function of y equals bx and y equals log bx has the y-axis. So the one we did from before, this created a y-intercept, this created an x-intercept, which makes sense because, again, they're switching the x and the y to get the inverse. Okay, limit as x approaches 0 from the right of a logarithm goes to negative infinity. So if I'm coming from the right, it approaches negative infinity because it drops down. So I'm coming from the right. Okay? Going to approaching infinity of the logarithm. So going to infinity, it goes to infinity. Now, why did it say approaching 0 from the right and not say negative infinity for the first one I told you? Right, because we can't go past this line. We can't have negatives there. Okay? Sure. Okay? So this is at 0 because we can't be negative. We can go to infinity, and it is infinity for when b is greater than 1. Remember, it's important for when b is greater than 1 because if b is greater than 1, that gives us the growth. If it's less between 0 and 1, that's the decline. That's the 1/4, the 1/2. So this is just telling you when you take the limit of a log, okay, as you're coming from the right, it's going to fall. Right, because we can't go negative. Right. We can't do a negative log because if our basis can't be negative, So like if my base was 3 and my exponent, there's no exponent a 3 can have that's going to make him be negative. So we can't ever have negatives there. No. 0, you can't take log of 0. That's why when we do our domains in a second, we're always going to start at 0, but be greater than, not equal to. Good. Okay. All right, so the diagram shows the relationship among the graphs of the logarithm functions 2, 3, and 5, and 10. So log base 2, log base 3, log base 5, and log base 10. So, good. Yeah, so that would just be these graphs here. Just kind of, I mean, you don't have to draw this if you don't want. It's in your book online or in your duotang, but just let you see what the pictures look like here. Okay. All right. Okay, so example 1. So let's find the domain of the function f of x log 10 to the x minus 3. So where do we want to really look at my domain? Because domain still goes with what, guys and gals? X, right? So we still want to look at what our x can be. Is there any restrictions on what we can take the log of? That's what Jeremy and I were talking about. We can't have 0 either. We can't have 0 or negatives. So that means what you want to do simply, this one's a little bit more straightforward, but if you're ever trying to find that, you just would say, okay, I know my x minus 3 has to be bigger than 0, so you write it as an inequality. X minus 3 greater than 0. Simply solve. Plus 3, x has to be greater than 3. So your domain is x greater than 3. Then it wants us to sketch the graph really quickly. So usually our vertical asymptote is where? If it was just x, where would it be? At 0. Now where's it at? 3. So we have an asymptote right here. So what I like to do is I always like to find the one that's going to be on the x-axis, my x-intercept, right? And that's always going to be the one that you get log of what? The other one. 1, because that's 0. Okay, so you just keep mixing them. So how do I get that to be a 1? A 4. So at 4, that should cross the x-axis. Because if I do 4 minus 3, I get 1. 10 to what power is 1? 0. That's why it happens, right? Okay, or am I saying that too much out loud? Do you want me to write it? So what I'm saying is, remember, this is y to us. Log 10 of 1. Or excuse me, I'm going to say, okay, let's go 4 minus 3. Of 4. 4 minus 3 is 1. 10 to the y equals 1. What's the y have to be? It has to be 0. That's why it's at 0 there. Okay, if you want to try some other ones and see how it grows, you can, but you'll get the idea that it's going to grow this way. I just like to use this as an anchor point because anything to the 0 power is 1. So that means when you do your logarithms, the base, right, when you plug 0 in for y, yes, that's right. But the reason this one's different, Dar, is because this one's x minus 3. So in order to make a 1 here, I have to use a 4. So that's why it goes to 4. Yes, absolutely, and that's how you're supposed to look at it. It's moved over right 3. Yep. Okay. Anything else here? Yes, except for I put a 4 in. See, I put the 4. 4 minus 3 gave me the 1. So it's not x. I plugged in a 4 for x. That's where the minus 3, that's what makes the shift. Okay. Anything else? Great questions. Stay with me. Okay, so now we're going to throw E into the mix. Because you guys talked about ln as well, correct or no? Math 30, no ln's. Okay, ln is simple then. ln is log, but with a base of e, that number we just learned about. You did? Okay. Log base e, see right here, is equivalent to ln of x. Okay? And it's in your calculator, it's just a way of doing it. Okay? It's just, and you know, e is still just a number, it's just the one we're going to use a lot because e is part of our exponential. Okay? That's the natural log ln, yes. Okay, so yeah, just all you gotta know is that ln is still a logarithm, but it's with a base e instead of 10 or 4. It's the base e. Yeah, I need to get a better definition of that. I really don't have a great one to tell you at the moment, but I'll figure out what actual e's definition is, and I'll figure it out and tell you. I know it has to do with exponential growth because exponentially things grow at a rate, and so it has something to do with that. But I'll try to get something a little more descriptive. So with that, e to the x and ln x are inverses. So that's, again, the same thing as we were just doing. Logs cancel, log with the same base cancels an exponent with the same base. Ln and e are like, they cancel each other. So those rules we just learned, those work for e and ln. Okay, and they're right here in these red boxes coming. Okay, any questions on that? Okay, so right here, conversely, ln e to the x is just x, because the ln and e cancel because it's log e. Okay, just like we just did from before. Like, I know that's an ln, but that's the same thing as this. We just talked about those would cancel. Same thing here. Those would cancel. E just with natural logs. Yeah, same rules. These numbers are kind of like the rules of the unit here. Okay, they also have the same relationship. ln x equals y is the same as e to the y equals x. So that, because we know this is a base e. Okay, whoops. It's a base e, that's the exponent, that's what it equals. Same pattern as logarithms. So essentially natural logs have the same rules and patterns as regular logarithms. Okay, so in particular, it's helpful to know that ln of e is just 1. Okay, just the same thing because that means e to the 1 equals e, which, yeah. Okay. That's the idea with e to the 0 equals 1. Okay. Is that okay? I mean, it's supposed to be the same, so hopefully just being ln's not confusing you. Okay, so let's look at one and why this helps us and how we're going to use it to solve. So it says solve for x. ln of x is 8. Okay, ln of x is 8. Well, what would you do here? What do you think? The thing that's helpful with this is that e is a number. That's not a variable, so we like getting e. Exactly. So that means e to the 8 equals x. E to the 8 equals x, and that's your answer. Okay, there's also another way I'm going to show you because we're going to, I just did the log rules. So no, it does not. ln is e. Every ln has a base e. They don't write the base anymore. Yeah. Okay. Okay, the other way I'm going to show you is important because you're going to use this to solve on stuff later. Okay, you don't have to do it here, but you're going to need to do it in general. If you're ever trying to get rid of an ln like that, you can, remember, in math, anything you do, you can always do to both sides. We're going to make everything have an e. So I'm going to go e to the ln of x equals e to the 8. And why did I do that? Right, because remember we just learned in our rules, that cancels. So that's a way that you can get rid of ln's if you need to. So we just e'd both sides, you could say. Okay? So that's a strategy that you will also use to solve things. Okay? And they got the same answer. And you want to use these when there's, like, this is fine, but what if I do, like, plus e to 3 here? Now you're kind of confused, right? Because it's not a simple pattern. So this one you're going to use a little bit more. Just like logging both sides, you can e both sides.
Why do you get to cancel the e and the ln?
Because that's what we talked about in the beginning, is that if you have something like this, okay, I could ln both sides. Ln is a log base e. Okay, so if I do this right, you see that? I can drop this now because it's an exponent. Ln of e is just 1, so it's just ln x now. Okay, ln of e, I can drop the 8. Okay, right, and then, so what would happen is that's 1 again, and so now I can do my thing I just did here, e to the 8 equals x. It all kind of comes together, okay? Anything else on that? Am I rattling your brain with natural logs? Too many letters? Okay, so solving this one. All right, so write that down and then just think, strategize, how can I get my x down? That x is up there, how can I get that down? This is where you need to take your mind, this is where you have to be good at for logarithms. How can I get it down? No takers? Yeah. ln both sides. So you're going to ln both sides like this. Because when you have, with your log rules, you drop the exponent in front. That's the move we want, because we want to get that down. Okay, so then we have 3 minus 2x ln of e equals ln of 4. Well, what do I know about that? ln of e is what? 1, so that's canceled. That means done. So that's gone. 3 minus 2x, remember we're solving for x, so don't lose track of what you're doing algebra-wise. Minus 3, not to the 4, these are separate. Divide by negative 2. That's an answer. You can calculate that. Okay, when you put that in your calculator, you get like 0.8, I believe.
Look at what we know about logs, and you say that e to the power of 4 equals 3 minus 2x.
E to the, no, it wouldn't be, no. Because I see what you're saying. You mean from here?
No, from the beginning.
From the beginning, so you want to write it. Oh, so you're saying, yeah, you could do that. Yeah, I see what you're saying. Yeah, you could switch that from here, and then you would just get to right here, right? Yeah, you could do that. Is that what you're saying?
Yeah.
You're saying that that's a base e, that's an exponent, so I know I'm going to equal my exponent, and then I'm going to be ln of 4. So yeah, that just put us right here. That's fine. You can do that as well. But again, as you get further, they're not going to make it this nice on you. You're going to have like other stuff here.
Yeah.
So it's not going to be as interchangeable. That's a good that you know that. That's fine. Okay?
So is it fair, like, the ln is like log base e and then you have an e?
ln is log base e and you have an e. Yeah. Yes. What do you mean that's okay? Sorry.
I don't know. It's just confusing. So like, it's like how do you know when to log both sides versus ln both sides?
ln. Whenever you see e's, you think ln's, because the ln's and e's are what cancel and go together.
So logging both sides is the same as like putting out, like you know how when we just do
Right.
logarithms,
When
they log both sides, it's like the same as doing ln both sides.
yeah, okay, ln's and logs are both logarithms. ln is just specific to e. Okay, so whenever you have e's or whenever you have bases of e, you want to use ln and not logs. Okay, but if you have a number, you want to use logarithms. Okay, so sketch the graphs of the following functions. So we're just going to look and see what happens here. So we already know what ln of x looks like. It's not quite what I wanted. So this one, I want to do more this way. This one I'll do more down the middle. Okay, so we're going to go to 1 here. Okay, no matter what, if I put in a 1 for my x, we know that's going to come out with a 0. There's no such thing as a plus or minus 0. Do you understand what I'm saying? If I put an x as 1, ln of 1 has to be e to the 0. What's that? Okay, so if you do this, we have y. We'll say we don't know what y is. Remember, what's the base of ln? So this is saying e to the y equals 1. Y has to be 0. So what I'm telling you is I'm going to draw the regular ln graph first. What's our regular ln graph look like? It comes from like here, right? Right. I know. I'm drawing the regular one. The negative one is going to. But I'm showing you they both would cover because there's no such thing as negative 0. Try to talk too fast. Okay. There's no such thing as negative 0. So they're both going to cross there. But the negative is just going to flip it, so it's going to come like, wait, did I do that right? Yeah, like this. Okay, and this is your negative ln of x. So what you can say from this is this, a, we'll write it right here, is a flip on the x-axis. For the 1 here?
Yeah.
But remember, 1 kicks out a 0. The negative doesn't matter because it's 0. Right. Because if I put a 1 here, that means that this side essentially is 0. So it's 0 negative or 0 positive, doesn't matter. But if you do the other stuff, it will switch. So like if we do e, so where's e? This is good. Where's e about? We said it's about, what's that decimal? 2.7. So right about here, right? So if I put a log e in here, that should be what? What's log e of e? 1. So on the regular ln of x, it's at 1. But the negative 1, it's now negative 1. Does that make sense? So that's where the flip is. Okay? All right, so with the second one here, I'll draw the regular again. So our regular is still right here. That's our regular ln of x look. So what would change on this one? Right, it's going to be a vertical flip. Because what happens is if I plug in 1, it's now a negative 1. Okay, so in order for this one to work, I have to plug in a what? A negative 1. A negative is a positive. Now I actually have that dot there. Okay, and then it's just going to be reflected the same and come down. So this one, part B, is reflected on the y-axis. Mm-hmm. Exactly, yep. Mm-hmm. This, like a parabola, flipped it. This, because it's on the inside of the brackets, affected the x. Okay, I know it affects the x, but it flips over the y, but it's still affecting the x. Very good. Yep. All right. Okay, so find the domain of this one, and we got to talk about one little thing here. I'm going to kind of go through this a little bit quickly because this is going to be a little confusing, but it's not super important. Okay, but so we still want to do what? 4 minus x squared still can't be what? We can't take the ln of 0, right? So we still want to do this. We still want to do that step, correct? And we're going to solve. Okay, so I'm at -4. Okay, divide by -1, makes me flip the inequality, and then square root. Okay? By square rooting, though, I get x less than 4, and then I also have the negative example. Whenever you're doing a plus or minus from a radical, you have to flip the inequality again. So you're, oh, 2, yeah, 2, sorry. 2, thanks. Less than 2 and greater than -2. Because when you do the negative example again, you have to flip again. So from our first couple weeks here, interval notation, that would be from -2 to 2. Because it's bigger than -2, but smaller than +2. Not including, because if we put it in there, that'd be 0, and we can't have 0. Okay? All right. Okay, so with that, limit, and this goes with the idea we already talked about earlier. Limit as x approaches 0 from the right of an ln, just like with the log, it can't go to negative, that's why it's a 0 from the right. It goes to -infinity. It drops off. Right? Same thing with this. So if I go back to this picture here, this is our regular ln. So I'm coming from the right, I go to -infinity. If I'm going to infinity, I go to infinity. Same relationship as the logarithm. That's what that last little thing is right here. Okay? All right. I'll try to hurry up here. All right. Okay, so find the limit as x is going from 2 to the left. Okay, so it's going 2 from the left. So with this, they kind of want to what they do is, because on our definition for that last page, if we do ln of x, we know that we would do, so I guess we want to look at it in these terms, rather than the 4 minus x squared. So what they do is on this, and like I said, I'm probably going to confuse you, but they're going to make this like be essentially t, and then they're going to say, they're going to go limit as x approaches 0 from the right of ln of t. Because in terms of 2, because if I was going 2 from the left, I would be coming, I'd be going towards the 0. Here, let me see if I can just pretend this is just like an x, and with our rules that we just learned, if we're going from the right, we would get the approaches. If we're going from the right of 0, what's the ln naturally do? -infinity, and so that was what the limit would be for this. So you would approach it in that aspect. I guess I'll try to figure out some more on that. That's probably true of why we can just call it from the right. That's fine. But the idea is that since we're taking the limit of something from the right of an ln function, that we know that limit would be -infinity based on that previous definition on the last page. Right. Yeah, so it would be approaching infinity. Right. Because ln's are either going to be going up forever or down forever. Okay, so then this part here is just like the simple rules that these are your log rules. It just show you that ln ones are the same. So remember, with multiplication of logs, you what? You add. Remember? Division of logs, you subtract. And then power to power, you can drop it. You can drop the power in front. That's just a review of your log rules, but just for ln rules. They're the same. Okay. I think I'll stop there just because the last two examples are just about change of base. So what I'll do is I'll just show you, remind you of it, but I'm not going to really go through it thoroughly because you should know change of base. Okay. Oh, wait, we want to do this, though. Okay, so there's just practice here. Express 1/2 ln of x as a single logarithm. So you're just doing all those rules and putting it together really quickly. So 1/2 I can put in front on the x. We're just pushing everything back. Okay, the 4 I can put on the y. Ln of x squared, I'll leave ln of x squared. Okay. All right, we'll do the second rules now. So then for, what do we have now? What do we do? So this is ln of x to the 1/2 minus. So divide. Okay, and then the other one's plus, so where does that one go? On top, yeah. And that's it. Since they all have ln's, you can get rid of the ln's, but you don't have to right now. Okay, so quickly to finish here. Here's the change of base. So the change of base is simply, if you ever want to change the base, you do the log of the, I don't know what you call that, log of that over the log of the base. Okay, and the b is just a common log, which would be, they usually do base 10 for your calculator. So that's just the change of base. And we will finish with that. What's this one? So this change of base again. Okay.